Thank you everyone for coming back for the last day, last lecture, which is exciting. Today I want to kind of wrap up everything that I started on the first day. And as I mentioned yesterday, we have a little bit more technicalities to get through, but then I want to connect all of this stuff up, Bridgement stability conditions on triangulated categories, blah, 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 back to the pointed pseudo-triangulations that we saw like in the first couple of lectures. Okay, so let me just begin, and I've taken a page out of Jodi's book and pre-written my lecture today just so that it's less pressure. And so what we have, I mentioned yesterday that if you have a triangulated category, whatever that is, you may sometimes have something nice, which is the heart of a bounded T structure on it, which helps you break that category up or objects of that category up along this heart. And then you're sort of reduced to just looking at objects in an abelian category, which makes your life a bit easier. So for convenience, I'm going to fix the heart of a bounded T structure on my category. And so recall that if you have a suitably nice abelian category, what you can do is you can write down a composition series for objects in your category, or you can write down a Jordan-Holder series. And once you do that, you can break up objects as decompositions of simple objects. And that's a really nice way to study the complexity of objects in your category. And that can often be quite hard, and that has lots of structure hidden inside of it. So you're breaking up your object into simple objects. And as I've written, it measures how complicated your object is. So if it has many simple objects in its composition series, it's a big object. And if the length is like just the number of simple objects, so you can measure things like that. This is great, but there's a slight problem with this. And the slight problem is that whether or not an object is simple heavily depends on the fact that your category is abelian. So if your abelian category is sitting inside of a big triangulated category, the object is simple in that abelian category. But if you change around your heart, a simple object may not remain simple. So you kind of lose. It's not like a triangulated invariant of the object. So, I mean, this may or may not be a problem based on your point of view, but it's a fact. And so there are many things that Bridgement stability conditions are good at. And one thing they're good at is kind of getting around this problem. So it's a way to measure the complexity of objects in your category, which is more amenable to the triangulatedness of the category, okay? So this is what, this is one point of view, which is quite powerful. So Bridgement stability conditions provide an alternate metric to measure complexity of objects in your category. And not only do they provide one, they provide, in fact, a family of them. So these are stability conditions that you can vary. If you vary the stability condition, you get different measures of complexity of objects in your category. And you should think of that as some kind of like souped up analog of like the length of an object in an abelian category. So there are various ways to do this. And one of the nice things is that there are various ways to do this. And then you can think about, if you vary your stability condition, what happens to the sizes of objects relative to what stability condition you're using. Okay, so this is kind of the idea, or I mean, one point of view. So let me give you some definitions, just so that we have something concrete to work with. So the first thing to recall is what's called the Grothendieck group of an abelian category. So it's a free abelian group on objects in that category, but then you impose the relation that the sum of two objects is a third object if they fit into a short exact sequence, okay? So if you have suitably nice categories, you need conditions on your category, but if you have suitably nice categories, the Grothendieck group is often generated by the simple objects in your category. So you could think, because every other object, as long as every other object is a finite extension of simples, you can say every object can be broken up into simples, and then the class of any other object is like the sum of the classes of whatever simple objects are in it. And so that's like telling you the length, basically, again. So this is what the growth in D group is. And a stability condition is going to be some piece of extra data on the growth in D group of your category. And again, for convenience, you have to remember that A is not just any old abelian category, it's sitting inside a triangulated category, and that's like, ultimately, we're interested in the bigger triangulated category, okay? But for now, for me, this A is a little bit of a crutch, and you can actually get rid of this crutch, but we're using it for convenience. So now, here's what a stability function is on your abelian category A. So what are we doing? We're saying, on one hand, we have this growth in D group, which has within it, objects inside of classes of objects inside of your category. And you're going to send every object or the class of every object to a complex number. Okay, but it has to be a group homomorphism. So C is an additive group and K of A is an additive group. And so this map, which is traditionally denoted Z, needs to satisfy whatever relations are true in the growth in D group. Okay, so if you have three things that fit into a short exact sequence, then the extreme terms have to add up to the middle term. Okay, and just there's an extra condition. The other thing I want here is that if I have any object in my abelian category, I want to send it to a complex number that lives in the upper half plane. So I'll draw a picture of this. So often it's very nice to just draw pictures of stability functions like this. When I say upper half plane, for me, it's always going to be a picture like this, where I include the positive real axis, but exclude the negative real axis. And sorry, also exclude 0. I mean, I'll keep it for now. But what I want is I want every object in my category, the class of every object, to be sent to some vector up here. Okay, so these might be objects in my category that go to various vectors in the upper half plane. And remember that this growth in D group is an abelian group. So if I have an object in my category, it also has a formal negative in the growth in D group, and that obviously should go to the negative vector, which is not in the upper half plane. Okay, so I'm only imposing this condition on actual objects in the category. Okay, very good. And then if I have a picture like this, so you should always be, for the purposes of this, what we're doing today, all of my stability functions I'll think of as pictures like this. And remember again that if your category is nice enough, if you have finitely many simple objects which generate the growth in D group, for example, you can choose to specify your function Z on just the classes of the generating simples. And then everything else is determined by additivity. Okay, so this is the reason why I'm drawing pictures like this. You should imagine that A, B, and C, little a, little b, and little c are maybe simple objects in the category, which as long as I specify what I want to do on those simple objects, everything else is determined. So it's a very concrete thing. You're drawing vectors in the plane for each simple object. Okay, great. And once I have a function like this, I can measure for every object whether or not it's semi-stable under this function. So what does that mean? It's a little bit of a technical condition, but it's something that's in principle checkable for every object. So if I have some object A in my category, I can check, is it semi-stable with respect to Z, or is it not semi-stable with respect to Z? And how do I check this? I look at every single sub-object, okay? And I try to draw, so let me draw a picture of this. So here's my, and I should have said this earlier, but of course, I mean, I'm just saying I'm sending objects to vectors. What I mean, of course, is that the classes of the objects in the growth in D group go to vectors, okay? But I'm ignoring that. So if I have some A here, which goes to, let's say, this vector in the upper half plane, I look at all of its sub-objects. Now, A is an object in the abelian category curly A, and so sub-objects make sense. So I look at all of its sub-objects. There may be many of them, maybe infinitely many of them, but fine, I have to check this condition. And I have to see where does it live in under this function Z, okay? And the condition is that all of the sub-objects have to live below the original object. This may or may not be true for a given object. Okay. One way in which it can be true trivially is if your chosen object was simple, because simple objects don't have sub-objects. I should say B should be non-zero. So I'm not worried about zero here. Okay, so if I started off with a simple object, there's nothing to check, and simple objects are therefore automatically stable. Other objects are more complicated. They will depend on what function Z you've chosen. Okay, so in principle, I can choose a Z, and then I can enumerate or check for every object, is it stable or sorry, I'll sometimes say stable, I mean semi-stable. Is it semi-stable or is it not semi-stable? Okay. And now the idea is that a stability condition is a function Z like this with a certain extra property. And the kind of measure of complexity of objects that I want under this stability condition is going to be roughly the following. How many semi-stable objects is my given object made of? Okay. So my object may be semi-stable already, in which case great. And if not, then there's a way to count how many semi-stable objects it has. And that's how I measure whether an object is big or small. So this is an analog of counting how many simple objects does my object have, but this is slightly different because I've imposed some extra thing. So here's now a definition, a stability condition on my category C, and now I'm saying in brackets, with respect to kind of my chosen heart A is a stability function which satisfies a certain extra property, which is called the Hardeners property or the HN property. And this is exactly saying that I can break up each object into semi-stable subquotients. Okay, so every object has a unique filtration into semi-stable subquotients, which kind of go in decreasing order. So don't expect you to like follow this right away, but the consequence of this is that each object can be broken up into pieces which are semi-stable, and not only that, this decomposition is a unique decomposition. Okay, so let's again go back to I want this really to be an analog of a Jordan-Holder series or something, but in some ways this is better because it's a unique decomposition. Remember that Jordan-Holder decompositions aren't unique. I mean, their filtration factors are unique, but unless you have some extra structure on the category, you can't say take the first Jordan-Holder filtration piece. There's not a way to do that unless you have something else floating around. But in this case, it's very nice because it's really the first kind of Hardeners piece and the second Hardeners piece makes sense. So this is going to be important somehow. Okay, I want to pause here. Are there any questions?
Do the definitions up to this point rely on C in an essential way, or could we repeat all of this just beginning with an abelian category?
Yeah, the question was, do the definitions up until this point rely on C in any meaningful way, or could we have just forgotten C? And so far, C hasn't shown up. So that's a great question. So far, C hasn't shown up, but I want to emphasize, and this is not going to be obvious because of the way I chose to present things, but all of this, you could simply choose to do just for A, and that would be fine. But there are kind of two reasons why C is going to be important. And one is that, first of all, okay, the category that I care about is triangulated. And so I need something for a triangulated category, fine. So that's one reason. But the other reason is that restricting yourself to kind of an abelian point of view is extremely restrictive. So ultimately, what we want to do in this whole story is, I've fixed A, but I want to, so there are kind of 2 points of view. So you can fix a heart A, and that helps with calculations because then it makes everything very explicit and you can kind of write down all the things. But on the other hand, it's kind of misleading because it seems like your definitions depend on what A you've chosen. The non-trivial or maybe non-obvious fact is that these definitions actually don't fundamentally depend on A. And so I can, even though I've chosen A as a kind of computational or convenience device, I could remove A from the story. There's an equivalent definition of stability conditions, which makes no reference to any bounded T structure. Okay, so this is really powerful. And this means that you can somehow, the equivalent definition tells you that, there's just some conditions on my category C, but then the bounded T structure is a consequence actually of the definitions. And then you can in fact have many different bounded T structures and you can go between them. So this is the beauty of the definition, which is not obvious based on the way I've chosen to present things. So sorry about that, but that's the choice. So this is my first remark. Sorry, did that answer the question? And yeah, was there another? That was the same question here. Okay. So the first remark, which again, as I said, is not obvious based on how I've presented things, this definition actually doesn't rely on A. So there's an entirely equivalent definition, which makes no reference to A, which would give you, which would kind of produce A out of the definition, okay? But can be easier to start with an A. The second remark, I already mentioned this, and I want to say a bit more about this. So when you write down, there's a couple of things to say. So if I've said that every object X inside of my abelian category acquires a unique filtration with certain semi-stable subquotients. Now, I'm really interested in objects of C. So how can I deal with objects of C? But remember, objects of C already have a filtration with respect to A. It's called the cohomology filtration with respect to A. So what I can do is I can take an arbitrary object of C, I can break it up along A, and then each piece, which actually lives in A or a shift of A, I can break up along its unique Hardeners filtration. So even though I've written that each object has a unique filtration only for objects in A, in fact, objects in C also inherit a unique Hardeners filtration. So I should have really written this, but so this Hardeners property implies that actually if you take any other object in the bigger category, you can first break it up along A and then break it up along this piece. So you get kind of a decomposition of any object with semi-stable pieces. And so you can measure any object of your category, of your bigger category, with respect to whatever stability function you've chosen on A. So once again, I want to emphasize that A is a crutch, but we will continue to use it for convenience. And the third remark is really fascinating. So the theorem of Bridgement is that if you actually look at the space of all stability conditions, now remember, this means I have to not just take my chosen heart A, but I have to sort of use the more invariant definition and take sort of all possible hearts of bounded T structures that can give you stability conditions on C. And if you take that big set, it actually has the structure of a manifold, a complex manifold. And this is a fundamental invariant of your triangulated category. So again, I apologize because we've kind of forced ourselves into choosing a heart and then going from there. And then this is all not obvious from that point of view. But if you kind of remove A from the equation and define everything simply in terms of C, you can see that if all of the stability conditions together have a nice topological structure. So this is really, really powerful because you can then move within that topological space. It's not a discrete set. And moving within that topological space kind of changes. So it changes quite a few things. It changes, as you move, it's going to change the Hardeners decompositions of your objects. It's going to change kind of the heart of the T structure that you chose. So you can start off with some heart and then kind of move within the space and then reach an entirely new heart. I mean, it's not rare, it happens very easily. And then you can, so lots of things can just kind of change around, but the powerful thing is that you can do this. Okay, so we want to play 2 games, maybe other games, but for the purposes of today's lecture, we want to play 2 games. So the first one is that we want to understand objects in C, sorry. So I haven't told you what C is. Oh, sorry. Yes, please. The question was, is it true that the complex manifold may not be separated? It's probably true. For the example that I'm about to present, it's not. I don't think that's a problem, but I can believe that in general. Is it for weird examples, you mean? Yeah. Yeah. So, okay. So let me comment on that. So Georgia is asking, the complex manifold you get may not be separated. And the point is the structure of the complex manifold comes from the fact that you're mapping the growth in D group over to the complex numbers, and the complex numbers have a complex structure, and you're kind of lifting this complex structure back. But the problem is that this map may not be a covering map. So it's like what's called a local homeomorphism. That's what Brisbane calls it in his paper, local homeomorphism, but it's not a covering map, and that can introduce some weird behavior. But that won't show up in the example that we have. Excellent. So yeah, so there are 2 things we can try to do. One is to just like look at various objects in C and figure out what they look like with respect to various stability conditions. And the other thing we can do is to like just look at the whole space of stability conditions and try to understand it. So I want to illustrate in the last portion of the talk where pointed pseudo triangulations make an appearance in both of these problems. Any other questions? Chris? Do we need strong finiteness properties to get number 3? Finiteness properties on what? Yeah, so typically for number 3, the question was, by the way, do we need strong finiteness properties to get number 3? The finiteness properties that you need are embedded in here. So if your categories are kind of small and the growth in D group is finitely generated and finite in some nice way, then fine, you don't need anything further. But in kind of algebraic geometric categories, you might have large growth in D groups, and then you impose extra conditions on what kinds of. So you impose conditions like this map has to factor through some finitely generated quotient group or something like that. Yeah. Otherwise, I think the result would still be true, but you'd get some like weird infinite dimensional manifold, I think. Okay. So let me introduce the category that we are going to play with. And I, just like many of the things that I've been discussing, I won't define all of it, but I will tell you what's important about it. So it's going to be the zigzag category of type A. The type A there is the Dinkin type A. You could, if you know what ADE means, etc., you can try to do this for other types, and analogous constructions exist, but I'm focusing on type A, which has strong connections to points in a plane, as I'll explain in a minute. Okay, so there's a triangulated category, which I'll call Cn for the purposes of this talk, and it has the following properties. So since we've been talking about T structures as a crutch, let me just say outright that it has a bounded T structure. Woohoo, so that's nice. And which I'll call the standard T structure. And its heart has n simple objects. Finitely many simples, even better. So n simple objects which in fact generate the Grothendieck group. And in fact, the Grothendieck group of this heart is isomorphic to the root lattice of type AN. Okay, so what does this mean? I mean, this means not only is there a bijection, but but there's, here we've seen in earlier talks, of course, that there's an action here of Sn, or is it Sn plus 1? Always get this wrong. Sn plus 1. And this bijection is compatible with the action of the symmetric group. And this bijection goes as follows. The generating objects P1, P2, P3 up to Pn map to the simple roots of type An. Okay. And so somehow if you are only looking at the Grothendieck group, it looks like the root system of type An, if you know what that is, and if not, that's fine. So this category upgrades the Sn action to something else, Sn plus 1, sorry. And so I may have a plus 1 wrong, I always get this wrong. Okay. So the Sn plus 1 action, correct me if I'm getting this wrong off by 1, but the symmetric group action on A upgrades to a braid group action on the entire triangulated category. So the triangulated category, I've already mentioned, these are like big categories. If you simply look at the Grothendieck group, you see an Sn action, Sn plus 1 action. And then on objects in my category Cn, the braid group actually acts. And this is an upgrade of the action that you see on the Grothendieck group. So I don't want to say too much about this, but practically what does this mean? This means that I introduced the braid group already. If you have an object in your category, if you start off with some X in your triangulated category, you can apply braids to this object and get new objects in the category. And typically, this action will move around quite a bit, so it won't keep you within the heart A. So even if you start off with some like easy objects such as Pn or P2 or P3 or whatever, and you act by various braids, the braid group is huge, and it's going to take you out of A. Okay, so it'll produce quite complicated objects as you act. So these are the three things that I want to say about this category in terms of like the categorical, or I mean, in lieu of the definition, let me just say. But now, okay, so what does this have to do with points in the plane, right? Because that's what we were thinking about. So this is a beautiful visual model of this category, and it's due to Kovanov and Seidel from like 20-something years ago, 20-ish years ago. So on the left, I have n plus 1 points in a straight line. Did I get this wrong again? I'm sorry, this should be Bn, right? Should be Bn? Jody? It's good, okay. There are n plus 1 points. So I think that part's fine. Yeah, very good, okay. It all solves itself. It starts at 0, goes to n. Very good, so good, Bn plus 1, everything is fine. So n plus 1 points in a straight line, and I've drawn them vertically in a straight line for a reason, which I'll explain later. But the point is, the visual model says you have your generating objects P1 through Pn, and each one corresponds to a certain arc in this configuration. So P1 is going to be the arc joining 0 to 1. P2 will be the arc joining 1 to 2, etc. Pn is the arc joining n minus 1 to n. Okay, so there is a correspondence which says objects, so the generating objects of my category can be drawn as arcs in this chosen configuration. And I told you that there's a braid group action on my category. And you also know that there's a braid group action on configurations and arcs in configurations. So you might wonder and probably conjecture correctly that the braid group action is kind of moves things equivariantly. Okay, so you can choose to act by the braid group either as the fundamental group of configuration space, or on the other hand, you could choose to act on objects in the category by the braid group, by whatever braid group action I haven't told you. And you should expect a correspondence. In fact, that this is the theorem. Okay, so this is the theorem of Cavano and Seidel. So if you have arcs in this configuration, and when I say arcs, it arcs as the ones that I mentioned before. So they start and end at different points, don't pass through any other points, up to isotopy, etc. So arcs in the configuration like this correspond to objects of Cn, not all objects, special objects. And those special objects are called spherical objects, and at the moment, I won't say more about that, just certain objects in the category, okay? But the point is, not only is there a one-to-one correspondence like this, the correspondence is equivariant with respect to the braid group action, okay? So on the left, I can act by Bn plus 1. Elements of Bn plus 1 can be realized as loops in the unordered configuration space. I can move my arc around with respect to that loop. I'll get some other arc. Now, from that other arc, based on this correspondence, I'm supposed to produce another object of my category Cn. And in fact, the object that I produce is the same one as the one I would have produced if I had acted on the braid group, by the braid group element on the original object in my category. So it's a very nice model. And the beauty of this model, of course, is that now I don't really need to think about objects in Cn. In some sense, I could sort of ignore them. Of course, not every object is captured by this, but enough objects are captured by this. And so I can now forget about technicalities of Cn and look at pictures of points in the plane, points and arcs in the plane. So that's where the points in the plane come in. Okay. So on one hand, this is a very special story. It's a particular category that I'm looking at, but on the other hand, the structure is very nice and very rich. So I hope you enjoy it. So now, so far, there are no, stability conditions or anything like that in the picture. And in fact, I drew the points on the left in a straight line, but as we know, there are many other configurations. So the question is, what do stability conditions on Cn look like visually? So, I mentioned, stability space is some kind of fundamental invariant of my category. It's a very natural construction. Can I somehow reflect that in the configurations? Can I somehow reflect that in the arcs? And yeah, that's the question. And the answer is actually surprisingly elementary. Okay, so it's very nice. So whatever follows is going to be joint work with Anand Devpurkar and Tony Licata. So here's some answers, or at least some of it is work in progress. So it's sort of being explored. So remember, our game number 1 was to measure the Hardener-Simon complexity of objects. And to do that, of course, I want to do this visually. So I want to tell you or explore or understand what stability conditions, first of all, look like as points in the plane. And it turns out that a stability condition, and I've written in parentheses with respect to A, just for convenience, is going to be simply a configuration of n plus 1 points in R2. So initially, I had chosen to draw just points in a straight line, but now you can vary that around. And in fact, the choice of varying the points around is exactly a stability function or a stability condition. And that's actually really not that hard to see. So here's why that's true. So here's on the left, I've chosen C4, and here's a stability condition on C4. So I'm allowed to put my simple generating objects wherever I like in the upper half plane. They have to satisfy the Hardeners Property, but that's actually that comes for free in this category. So I don't have to worry about it. So I've simply placed, P1, P2, P3, and P4, wherever I like. And now how do I get a configuration of points out of it? Well, I start off with some point, and then I start drawing my vectors P1, P2, P3, and P4. So I go, from 0, I go P1, P2, P3, and P4. So I just like trace them in a straight line. And let's assume for simplicity that my stability function is generic in the sense that I don't have vectors colliding. Okay, so if I don't have vectors colliding, then on the right-hand side, I'm not going to have points, collinear points, right? So you can check that. But like this procedure, very simple procedure, produces a configuration. So great. And then you might wonder, like, if I've given you a configuration, how do you go back to a stability function like this? And that's actually also not too hard to do. I'll leave that as an exercise. So you can actually go back and forth. And then, yeah, actually, I won't say anything. So this is fine. And now I want to think about, okay, I have a stability condition. Once I have a stability condition, the important thing is which objects are semi-stable. So I have to try and recognize semi-stable objects and like, can I do that also in this picture? And it turns out that you can. So the semi-stable objects in the stability condition that you choose on the left are just straight line arcs in the configuration that you get. Okay, so here's one example. So I haven't told you anything about this category, so you'll just have to believe me. But if I have my generating object P2 and P3, there's actually a semi-stable object here whose class is the sum of these two. In fact, it corresponds to the positive root in type A, which is alpha 2 plus alpha 3, if you like. I mean, the sum of those two simple roots. But there is a semi-stable object which lives there. And how do you see it in the configuration? Well, you know that P2 and P3 were vectors that you traced. So this was P2 and this was P3. And it's their sum, okay? So remember that arcs in this configuration are honest objects of your category. And in fact, the straight line ones, there are going to be finitely many of these straight line ones. Those are exactly the semi-stable ones. So this is not, well, this is almost correct, but I should be a bit more specific, indecomposable semi-stable objects. But it's not a big deal. Okay, so essentially all of the semi-stable objects that you care about, the indecomposable ones, are captured by straight line arcs in the configuration. And this tells you, and this is not a new theorem, but it tells you once again that there are n choose 2 of them, or n plus 1 choose 2 of them. Again, sorry if the indexing is off by 1. Okay, so this is nice. And so now I have a handle on what stability conditions look like visually. I have a handle on what semi-stable objects look like visually. So now I'm ready to translate what happens if I have some weird complicated object, which I'm going to restrict myself to spherical objects, which are the objects that I can draw as arcs in the plane. So if I draw a weird complicated arc in the plane, how can I decompose it along its Hardeners infiltration? And so we've already seen how to do that in without reference to stability conditions somehow. So, so it's maybe what you thought it was. So if you take some complicated object, which looks like some complicated arc in the plane, and you want to figure out what are the semi-stable objects that appear in its Hardeners infiltration. So then you just, you take the support of the corresponding arc, like we were doing yesterday. So you figure out, if you pull this arc tight, which of the edges show up. So maybe this one shows up, etc. So I've drawn that on the right. And not only that, you can do a bit better. You can say that some edges show up twice. You can write down the multiplicities on each edge. So this one shows up twice, etc. And others show up once. So in fact, whatever this object is on the left, using this Khovanov-Seidel recipe, you can write down exactly what that object is. You can say, okay, here's a stability condition. I know how to decompose my object in terms of this stability condition into its unique Hardeners filtration. It's going to have some semi-stable factors, and the factors that I get are exactly these ones with these multiplicities. So this is a complete picture of how to, so you take your spherical object and you reduce it to a bunch of numbers on a pointed pseudo-triangulation, minus an external edge. Okay, so as we have seen in the course so far, pictures like this are going to live on pointed pseudo-triangulations minus an outside edge. So let me write that. Okay, so this is where the pointed pseudo-triangulations come in naturally, because you get a configuration and then the moment you start studying objects, you get PPTs as their support. What did I want to say about this? Oh, right. And so now you can do something cool. So what you can do is, as you see, I mean, I've fixed this particular PPT, and I have certain multiplicities on each edge. And you can ask things like, okay, I have this object on the left here. I know that I can act by elements of the braid group. If I act by some element of the braid group, can I figure out how these numbers change? So this is the thing on the right is a combinatorial skeleton of the object on the left. And you might ask, like, can you describe, you know exactly how the braid group acts on the left, but it's quite complicated. But can you just describe that in terms of numbers? So that's a reasonable question. And to answer a question like this, so notice that I have these numbers. So what I can do is I can make a simplicial complex out of all of these different pictures. So if I fix a configuration, I have finitely many pointed pseudo-triangulations minus outside edges in it. And I can make a simplicial complex where these are the maximal simplices. Okay, so here's a picture of, so my configuration here is 4 points in a square. And if I draw all of the possible PPTs minus outside edges, I get 8 different possibilities. So these are my maximal simplices. And how do you create a abstract simplicial complex out of something like this? Well, this one has 4 edges, and this one has 4 edges. And then if I intersect these two, I look at the common edges. Okay, so this gives me a set of 4 elements, namely the 4 edges, gives me a 3-dimensional simplex. So this is a general recipe for creating a simplicial complex, or the geometric realization of a simplicial complex, if you like. So this is a 3-dimensional simplex. This is a 3-dimensional simplex. This is a 3-dimensional simplex. There are 8 3-dimensional simplices. And if you intersect 2 of them, they may have some common edges. And depending on the number of common edges, that's like the dimension of the intersection. So if you think about these two, I have these 3 common edges, and so that's a 2 simplex. So these 3 simplices intersect along a 2 simplex. So that's how I would create the geometric realization of this kind of simplicial complex of pointed pseudo-triangulations. And so my recipe here is telling me, if I take my favorite spherical object, I draw it as an arc, I pull it tight, I get some numbers, I put those numbers, so these are the weights for each of the edges. So, I'll get a point in this abstract, I'll get a point in this simplicial complex corresponding to the weights 1, 1, 1, 1, 2, and 2. Okay, so that's a rational point on my simplex. Does that make sense? Any questions? Oh, yeah, so when I say, I should have really said, I'm looking at this abstract simplicial complex and I'm taking its geometric realization. So I'm thinking of this object here as a 3 simplex, which lives in some big real space, R3, let's say. And so rational points are, so if I assign integer weights to each edge, I'll get some point inside of this 3 simplex, which has rational coordinates. Right? Because I'm looking, so the way the translation goes is I have a weight for each edge, which could have been a real number, but if I start off with an honest curve, it's always going to be an integer, in fact, a positive integer, right? And so a positive integer weight up to kind of a simultaneous scalar. So that's how I get from, so I haven't explained any of this, so I apologize, but the way I get from a picture like this to a 3 simplex is I look at the tuple of all of these weights up to simultaneous positive scalar. And so if I have an integer for each edge here, I'm going to get a rational point inside of the corresponding 3 simplex. Okay, so each. Sure. Yeah. Yeah. Another way to say it is to take the coordinates and divide them by the number of edges. So you could do that. So each bit here is going to look like a tetrahedron. So a point on the tetrahedron corresponds to a choice of weights, 1 for each edge. And so all of these tetrahedra glue together to form something. And all of my objects live on that gadget via the Hardeners in multiplicity. So now you can imagine this all changes dramatically if I change the stability condition. Okay, so it changes. Okay, but let me move on. So let me not say anything about this, but the braid group action is fascinating to study because like there's a combinatorial like skeleton of the braid group, of the objects, and the braid group is supposed to act on the object. So how does the braid group act on this simplicial complex? So it's a fascinating question. And then the game number 2, and I'll say this quickly, game number 2 was to think about what this whole space of stability conditions looks like. So it turns out, and I'm not going to say much about this, but a point in the space of stability conditions is simply a configuration plus an AN chain of arcs. So something like this. So a configuration of points, and then arcs that connect 0 to 1, 1 to 2, 2 to 3, 3 to 4, and 4 to 5. Okay, so here's another one, 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5. So a gadget like this corresponds precisely to any other point in the stability condition, maybe up to some epsilon thing. And notice that each of these lives on a pointed pseudo triangulation minus an external edge. And we've seen, because of the rigidity stuff, that PPTs minus external edges have a 1 degree of freedom expansively. So now what you can do is you can take one of these gadgets, you have a degree of freedom that expands your gadget, and so you kind of expand it. And as you do this, it's going to unwind this chain of arcs. So you kind of like, this is basically Strynew's algorithm for the Carpenter's rule problem, but you're doing it in a slightly more sophisticated way because you have these arcs now. So this is somehow an upgraded version of Strynew's algorithm kind of unwinds everything and gives you an explicit contraction of the space of stability conditions down to a point. So this is cool because like you've started off somewhere far away and you have a procedure to unwind without breaking anything to come back to some like starting point. So this is not a new theorem, it's a new proof of a known result. So it's not, so stability space of Cn is contractible, but this is the direct proof. And I just want to say at the end, like one remark, as I mentioned, this is all super specific to the particular category that I chose, but you can try to do this. I mean, this is maybe game number 3, which I haven't said anything about, but you could imagine now having other categories which have no connection to configuration spaces, but kind of trying to do rigidity directly on the category. So that's like something you might think about, because like it is, you have, this this stability function is a function that maps to C, and vectors in C, you can kind of think about rigidity. So vectors in C, you can do calculus on, I don't know. So you might think there's a way to do rigidity directly on your favorite category, which has nothing to do with configuration spaces. So this is a question. Okay, but I'll stop here. Thank you so much.
I have a question.
Yes, Hawaii.
So the filtrations carry an order. Do you lose that order when you do these diagrams?
Yeah, that's an excellent question. The question was the filtrations carry an order, and how do you see that in the diagram? I didn't explain how to see it in the diagram, but it is in fact possible to recover the exact filtration, not just the support. So you can. If someone, if you start off here and you produce a list of numbers like this, I can actually take just this list of numbers and go back to the curve, and that's a bit more work, but it can be done.
Thanks.
Sure. The question was, if you take a meromorphic function on your space of stability conditions, does that have a... Is there some way to interpret that as a combinatorial? Yeah, does it have a combinatorial like interpretation? That's a good question. I don't know. Yeah, it's I guess it depends on how you describe that function. How you, because like it's, if I want to describe a meromorphic function on stability manifold, I have to understand something about the stability manifold maybe, but yeah, it's a good question. I don't know. Chris? Second last. Yeah, so and this is what I'm about to say is true, like up to like some epsilon that I'll hide. But if I have a point in my stability manifold, I can actually think of a point in the stability manifold as simply a configuration of points in the plane, so n+1 points in the plane, but not just that. So just going down to a configuration loses a lot of information. But if I want to actually recover what stability condition I'm coming from, I also need the data of what I'm calling an AN chain of arcs. So I have n arcs that go from 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 5, and 5 to 6, etc. So remember that why should this be true? So if the stability conditions that we were looking at here were with respect to a fixed heart A, and then this is the AN chain. And I mentioned that you can, so this is why stability conditions of this specific type are simply configurations, because you can kind of actually recover the AN chain. But more generally, you have other stability conditions which don't behave well. I mean, they aren't like with respect to the heart A, they're with respect to some other heart. And then you have some, and then to describe such a thing, you need a configuration, but you also need a chain, which goes in a more complicated. Yeah, the question was, is this like a test case where you can do everything you want with your stability conditions? I think the answer is yes, yeah. Here, you have this visual model which allows you to do all kinds of things, and you can, you can either use, like whatever theorem you want to prove, you can either say, okay, let me do it categorically, or let me not do it categorically, let me draw pictures of it and see if I can prove it topologically. So you have these, like a very strong correspondence, and in other situations you don't, so you have to do other things. Are there other triangulated categories for which the space of stability conditions is restricted but interpretable in this language? So not in this language necessarily, but there are lots of papers on like triangulated categories where people have been able to compute the space of stability conditions using like other combinatorics shows up probably, but like, yeah, there are papers, yeah, there are results, but not this specific thing, maybe. Yeah. Jody says the connectedness issue of stability space is a massive issue. Connectedness and contractibility. So this is a big in general, if you have your favorite category, you might ask like, what kinds of properties does the stability manifold have? And it's not even known in general if it's connected. It would be nice if many of them were contractible, but these are questions, which, and it seems so far, it seems that there isn't a unified technique to answer them. Like there's sort of various, you pick your favorite category, you do something and you hope that you can show connectedness, etc. There are some techniques, but they're sort of not, there isn't one tool that you can use. Is anything known about which complex manifolds can arise as stability conditions? Very little. So many of them are just either, some of them are empty. So some categories just don't have any stability conditions, but some of them, many of them are just known to be like R2 or something like that, or C2. Yeah, just kind of most examples are sort of contractible. So the question was, is it easy to tell if the manifold is even non-empty? And in general, I mean, the category that I presented here is super nice. It has like extremely nice symmetries, etc. And in that case, you can just write things down. But if you have larger categories that don't have finitely many simples, if your growth entity group isn't generated by simples, you run into complications because how do you even write down a stability condition? You're supposed to write down the stability function, but if you have too many objects in the heart, then how do you even write it down? And yeah, so even those questions can be difficult for bigger categories. What's an easy, nice example of a growth entity group? I mean, if sure, I'm not sure. Yeah, what's an easy, nice example of a growth entity group? I'm not sure what you're looking for, but like, if you look at the category that I had in the exercises yesterday, it has two simple objects, and so the growth entity group is that too. You can look at the category of vector spaces, which is generated by one simple object. Yeah, I mean. Yeah, thank you, Joel. Sorry. Sorry, Chris. So yeah, let's all just give Asilata a huge round of applause. Thank you.
Yes, on behalf of I'd like to say thank you for coming on and giving the week. Yeah, it's big number one. Very fun, but also very valuable. Being honest, it's something you can study these things for 6 months or a year, not realize 7 years, pick it up in 2 weeks. So yeah, thanks for lighting up.
Thanks.
Thank you very much from Hawaii too. It was a very enjoyable class, easy to follow, and very playful.
Thanks, guys. Thanks for coming.
Thanks, Asilata.